All right. So section 9.6 deals with alternating series. We've actually looked at a couple of alternating series before. And remember, those are series where all the terms go back and forth between positive and negative. So we add something, subtract something, add something. So some alternating series, we're going to be able to tell whether they converge just by using some of the other stuff we've already looked at. So, for example, an alternating geometric series, right? R is allowed to be negative in those series, so we don't need any kind of special test. We can actually not only tell that they converge, we can sum them up and find the sum. But some alternating series are just too difficult the way that they're constructed to do that. So we actually have a test called the alternating series test that we can apply. So the way that you identify an alternating series is it will always contain a term, right, of like -1 raised to some stuff, okay? And so that term in the series is what's going to make it bounce back and forth between positive and negative. So if we were to look, and there's kind of two most common forms of the stuff that ends up in the exponent. So if you look at n equals 1, and your term in your series is -1 to the n, right? What that means is all the odd terms will come out as negative, right? And the even terms will come out as positive. And what I mean by odd and even is the order of the term in the series, not even and odd numbers. Okay? Even an odd index, right? If you've got n equals -1 and your term is -1 to the n plus 1, well, what that does, adding that +1 in the exponent, is it shifts the negative sign over by 1. So now all the odd index terms would come out positive because you would be adding 1 to an odd number to make it even, right? And the even terms would come out negative. So if you're constructing a series, excuse me, or you're trying to build the nth term off a pattern, you can simply use that method to shift the negative sign backward or forward however you want, right? You could also have -1 to the n minus 1. That would also do a shift for you, okay? The only thing you would have to be careful with there is, you know, we don't really use n minus 1 if we're indexing from 0, because you don't want your first exponent to be negative, even though -1 to the -1 is just 1 over -1. So you have a lot of options when you're trying to create an alternating series term. So let's look at our old friend that I told you we would just be all sick of by the test. So if I write this series like this, right? This is an alternating geometric series, right? It's -1/2 to the n. We know this converges. It's a geometric series, and we could sum it up. We would just say 1 over 1 plus 1/2 if we're counting from 0. But we could rewrite this and put it in the form of an alternating series. So if we wanted to rewrite this to make it look more like a traditional alternating series, we would need to have the -1 out front. So I can simply say, well, this is -1 to the n over 2 to the n. So -1 to the n times 1/2 to the n. Those are equivalent series. And we know the terms, right, are going to look like this. So don't forget a really important property of exponents. If you have two things being multiplied together raised to an exponent, you're allowed to rewrite it as each individual thing raised to that same exponent, right? And they get multiplied together. Similarly, if you start with this and you need to combine them, you're allowed to combine them back. And this rule also applies when you're dividing. If you have x over y, right, to the n. I saw a lot of people struggling with this on the quiz, right? That is the same thing, right, as x to the n over y to the n. So if you're trying to create a geometric series, you're probably going to be in this situation and write it back like that because you want to find the r value. If you're looking at playing around with alternating series or rewriting them, you may have to factor the -1 up to the stuff out front. So let's look at what the alternating series test actually does. So this is kind of like the direct comparison test in the sense of there isn't really a lot of math, like, or what you guys would consider computation involved. It's really, does the series fit 3 conditions? And if it fits the 3 conditions, it converges. So you're just basically running down a checklist. Does it do this? Does it do this? Does it do this? So let's see what those conditions are. So let A sub n be greater than 0. Oops. And this is really the first condition. It's just sort of implied in the definition. But then the alternating series So what you have to make sure you're understanding when you read this is the alternating series test. So it applies to alternating series. So it is implied by definition that this -1 will be out front. And so the reason they give you both forms is they're saying, well, it doesn't matter where the negative signs start, right? This could start at the first term. This could shift it over by 1. So what they're talking about when they talk about A sub n is all the stuff that doesn't include the negative term. So they're saying, look, we already know it alternates. Take the -1 away. Look at everything else you have. If that stuff is still positive, right, then you can proceed. If that stuff is not positive, then you might be able to factor more negative stuff out to get it in this form. Okay, and I'm going to show you some examples. So then it says, well, if the limit of the stuff that's left over goes to 0 and the terms are decreasing, right, for all n, then it's going to converge. Okay, so let's look at an example of how to apply this test. So we're going to apply this to our series we just looked at, right? The alternating geometric series. Okay, so this is -1. This part, everything that's not the -1 term, that's your A sub n. So they're saying that A sub n, right, is 1/2 to the n. That is in fact positive, so that checks out. The limit of that term does indeed go to 0. So check on that, right? Then it says, well, are the terms decreasing? So in order to determine whether the terms are decreasing, all we have to do is look at the nth plus 1 term and compare it to the nth term. So I remember I put the little empty box there because I'm not really sure about the inequality. I'm leaving it open. So we can rewrite the term on the left as 1/2 times 1/2 to the n. Right? So, right, it remembers you can add the exponents together if they're written separately, and you can also break them apart. So now my 1/2 to the n cancels on both sides, and I'm left with 1/2 and 1, right? Because there's an implied 1 times right here. So this is in fact less than or equal. So condition 3 checks out. So this thing converges. So obviously, if we actually had this series on an exam, my hope would be the most efficient way is you would recognize this geometric and you would just say it converges that way. That's a really simple way of doing it. But I want you to see that 1 over 2 to the n can handle pretty much every single test we're going to show you. So it's a really good series when you're practicing how to apply the tests and the conditions to test out, because you make sure you understand what's happening, and you should always come to the same conclusion that things converge. Right? Is there any questions about this? You guys get the 3 conditions now? So the thing I've been noticing at Millage when people are working with these is when they want to apply the alternating series test, they keep leaving the -1 in the picture. And the idea is, no, we know it's alternating, so you just shove it aside and you're dealing with everything else. Okay? All right, let's look at another one. So this is the alternating harmonic series. We've already discovered that this thing converges. So it should pass the alternating series test. So the first thing is our term a sub n, right, is just 1 over n because we ignore the -1. Those terms are positive, so it checks out. Then we take the limit of a sub n, or that equals 0, so that checks out. And then we want to know, well, does the nth plus 1 term, how does it compare to the nth term? Well, clearly, right, the numerators are the same, so we don't have to worry about that. Clearly, if you make the denominator of a fraction bigger, it gets smaller. So we can actually just see from this initial setup that they are, in fact, going to decrease over time. So it passes the 3rd condition, so we can say the series converges. So let's look at a series where it doesn't look like it's alternating and we have to rewrite it to put it in the form to make it alternate, right? And this is really where this first condition comes in. If your a sub n is not positive, then I was saying before, you may not have factored out the negative stuff properly. Okay, so that's -2 to the n minus 1. So I'm allowed to say, right, that this is really -1 times 2, right? And since it's raised to the n minus 1, I'm actually allowed to say this is -1 to the n minus 1, right? Because we said we had that property that if you have 2 things being multiplied, right, we can set them up. So since -1 doesn't really matter if it's in the denominator or the numerator, I'm allowed to pull it up to the numerator. So I can rewrite this as -1 to the n minus 1, and that leaves me with just n over 2 to the n minus 1. Does anybody not get that algebra move? We're good? Okay. So now I have another form where all the negative stuff's out front and I just have to deal with the term that's left. So our a sub n term is just n over 2n minus 1. Those terms are positive. The limit of this is clearly 0 because that exponential on the denominator is going to dominate that n in the numerator. And so now I just need to verify that the terms are decreasing. So n plus 1, right, I got to plug in n plus 1, over 2. Now look what happens here. If I plug n plus 1 in for n, I'll get n plus 1 minus 1, so that 1s will cancel out, and you just get 2 to the n. Yep?
Where are you getting that?
So one of the conditions is that the nth plus 1 term, which would be the next term, is smaller than the previous term. So when you want to, right, see that? So this is a sub n plus 1. So you just plug in n plus 1 everywhere you have an n, right? And then here, right, that's what a sub n is. So if this is less than or equal to this, we're good. So this one's not quite so obvious because the numerator on the left is bigger than the numerator on the right. So we can do a little bit of algebra to test this out. Since all of these terms are positive, every piece of this is going to be positive, I'm allowed to multiply and divide things all day without reversing the inequality. So I know the inequality stays intact. So what I'm going to do is I'm going to stack the like stuff on top of each other. I'm going to take the 2 to the n minus 1 and multiply it both sides and put it in the numerator. Then I'm going to take the n plus 1 and I'm going to divide by both sides to bring it over here. So I can now say 2 to the n minus 1 over 2 to the n. How does that compare to n over n plus 1? All right. Furthermore, I'm going to take this guy right here and I'm going to break it up. So we're just going to continue this over here. So I can say, well, 2 to the n times 2 to the negative 1 over 2 to the n. I'm going to leave this alone for a second. And my 2 to the n's cancel. Furthermore, 2 to the negative 1 is just 1/2. So now I need to know, well, what does this do for all n? So if you go back to the original series, n started at 1. So if I plug in a 1 right here, I get 1/2. If I were to plug in a 2, I would get 2/3, okay? So this is in fact less than or equal to, and since I didn't do anything that would have flipped the sign along the way, I know that I can backfill in my inequality signs, and this does in fact reduce over time, so this series converges.
So if you're starting at 0, you wouldn't be able to do that?
No, and we construct, make sure, well, also you would have had an issue because if you started at 0, that would have shoved the first number back up into the numerator. But generally we start series from 1. And then there's special cases that we start from 0, like geometric and things like that. But you'll see most of the series index from 1. Yeah, but no, that's a good question. Anything else? All right, so let's look at another one. So this is definitely an alternating series. Our a sub n term is n plus 1 over n. Those will be positive. But when we calculate the limit of n plus 1 over n, what do we get? 1. Not 0. It fails the first condition. Furthermore, if we check the second condition, when you plug in n plus 1, you're going to get n plus 1 plus 1, so that becomes n plus 2 over n plus 1. And when you compare that to this, what I can do is I can cross multiply. So when you cross multiply, we end up getting n squared plus 2n. So when I multiply n plus 2 times n, and then I'd have n plus 1 squared. So that gives me n squared plus 2n plus 1. Well, you can subtract n squared from both sides. You can subtract 2n from both sides. And you get 0 is less than or equal to 1. So it passes the second condition, but it failed the first condition, that the limit had to go to 0. So the alternating series test does not apply. Right? Fails the first, passes the second. But we can actually see, because of the limit up here, that this thing is going to diverge. because all the -1 was going to do to this series is make those terms as you went to infinity alternate between 1 and -1, because that's what the result of the limit was. So you basically have a series that as the numbers get really big just are 1, -1, 1, -1, 1, -1, and we learned way back that those limits don't really even exist, right? You can't find the limit because it all depends on where you stop counting. So every -1 wipes out a 1, right? But if the last term is -1, the series would sum to -1. If the last term works out to be 1, the series would sum to 0. So how do you know what the sum is? So even if you looked at the sequence of partial sums, you would see that the sequence of partial sums just go 0, 1, or 0, -1, 0, -1, 0, -1. So this thing cannot converge, so it's going to diverge. So I wanted you to see an example of something where it fails this test. So don't assume that all alternating series will converge. Yeah, question?
On the first example,
Uh-huh.
we didn't cross multiply, but we were canceling things out on each side of the equality.
Mm-hmm.
One half of the end got crossed out on each side.
Uh-huh.
But it's still one on the other side, so it's one half and one on the other side.
Yeah. So the question is, why did this become a 0 versus here, why did this become a 1? Okay? So here, I was dividing both sides by 2 to the n. Here, I was subtracting the terms from either side. You see the difference? So when you multiply, the opposite is divide. So 2 to the n over 2 to the n became 1. Here, I was subtracting. And so when you subtract everything away, you're left with a 0. Right? Question? Yeah, okay, so the question was, if it passes the alternating series test, it converges, but if it fails, does it diverge? So if it passes 100%, it converges, okay? If it fails, you kind of have to look at why it's failing to figure out if it diverges. If the limit of the a sub n term is not 0, it's going to diverge, right? Just for exactly what I said, because that means, and then it won't only diverge, but then the alternating thing, right? So if it was a normal series without the -1, we would just say, well, this thing diverges because it eventually just becomes 1, 1, 1, 1, 1. The alternating term then makes it go back and forth between 1 and -1, right? So if the limit had been 2, then we know that the series would have been 2, -2, 2, -2, 2, -2. So it would have diverged. So whenever that's happening, it's a diverging sequence. If the terms are not decreasing, but it's the limit's going to 0, then we probably need to try another test to confirm. But more likely than not, if it's an alternating series and it's not passing this, it's probably going to diverge, but you would have to inspect. So it sort of kind of depends on why it's failing. But the limit failure is almost always going to mean diverging. Right? Well, actually, it will mean diverging, right? All right. Any other questions on these before we move on? Okay. So it really is just learning the the checklist you have to apply and making sure that you're doing that, all right? So the next question though is, can we find the sum of an alternating series? So not exactly. I mean, we can sometimes, right? But we can actually estimate it pretty closely, right? And this is not something I'm gonna make you do on the exam, but it's something that you need to see, because if you ever apply series in any other classes, I have a former student I ran into last night who's now in discrete math, and like they've been dealing with some series and summation in there. So especially if you're in computer science, this stuff comes up a lot. So one of the things that you have to know is, how do you find the sum? And we can deal with something called the remainder, okay? So in order to understand this, right, remember that S sub n was the sum of the first n terms. So the remainder should be the sum of the entire series minus the sum of the first n terms. So if you like actually by hand add up, like pick an n and add up those n terms, well then you know that everything that you have left over is just the total sum minus that stuff, okay? So there's a theorem that says how we can calculate the remainder. And we can use the remainder to get us in the ballpark of what the series might actually sum to. So first the series has to converge, because if it doesn't converge, the sum doesn't exist, okay, or the sum's infinity. So first we have to have a convergent alternating series. And that means in order for it to pass the alternating series test, right, the terms had to be decreasing, right, once we took rid of the negative stuff. Now I'm going to show you an example of what this means too. This is very wordy. Okay, so all of that to say this equation. So I'll let you guys get this down and we'll talk about it. So this is actually a really complicated way of expressing a really simple idea. It's actually pretty neat. We'll work one out and you'll see it. Okay, so what we're saying here, right, we've already established that the remainder, right, is equal to the sum minus the sum of the first n terms, right? Then what we've said is, well, if you take the absolute value of both sides of that equation, that's a legitimate math thing. If the terms are steadily decreasing, it's saying that the absolute value of this will be less than or equal to the a sub n term. The reason we have to take the absolute value is the a sub n term is positive because we take out the negative stuff. And those terms are alternating. So depending on which value of n you pick, the next term could have been positive or it could have been negative. So it's like, let's just look at the magnitude of the number, all right? So let's look at an example of how you would actually apply this. And when you see some numbers, it actually makes pretty good sense. So if we look at the alternating series, -1 to the n plus 1 times 1 over n factorial. This series is going to look like this.
Sorry, there's something wrong.
My sister made her years ago start calling me Boo. So she's like, sorry, Boo, I can't. But then I didn't know if like you're on Apple and you like send somebody a message on like their iPad or their iPhone, my name will show up as Boo. And so it was so funny. My one friend was like, yeah, my girlfriend wanted to know why Boo was texting me on my phone. I was like, oh God, sorry, that's me. My sister did that. All right. Okay, so this is the first 6 terms of this series. This series is going to converge.
Here's what I found on the web for is going to converge.
It's going to converge by the alternating series test. Right? The limit as n goes to infinity of 1 over n factorial is 0. And we can see by looking at the series, right, that the terms are in fact decreasing. So we know this thing converges. So if we want to estimate the sum of this series, we can pick any n we want. So I just picked 6 because I wanted to sum it out for a bit. So the sum of the first 6 terms, right, is 1 minus a half plus a sixth minus 1 over 24 plus 1 over 120 minus 1 over 720. And when you add those up, you get 91 over 144. And that is approximately equal to 0.63194. So those are just adding up the first 6 terms. So using our theorem, the absolute value of the sum minus those first 6 terms should equal the remainder. So what R6 means, it means the remainder means that is the value of terms 7 through infinity. Okay, because we subtracted off 6 from the sum. So this should be less than or equal to term A7, right? Because it said go to the next term. So term A7 would be 1 over 7 factorial. And 1 over 7 factorial is 1 over 5,040, which works out to be roughly 0.0002. So what that's saying is terms 7 through infinity add up to about 0.0002. Okay? And what we can then say about this is if you take an inequality and you have the absolute value, so if I'm saying, if I want to solve this inequality, R6 is less than or equal to positive S, wait, I'm sorry, I'm doing this backwards. If I go back, sorry, I'm real bad real quick right here. If we go all the way back to this equation, if I add S6 to both sides, the total sum, it should be the remainder plus the sum of the first n terms. Does everybody see that? Okay. So if we come down here, this number could be positive or negative, right? Because the remaining terms could add up to be a positive value. The remaining terms could add up to be a negative value because they're alternating. So the sum is somewhere between S6 plus R6 if it's positive, or it could be the sum of the first 6 terms minus that guy if it's negative. And so that means if I take our sum here of 0.63194 and subtract this from it, I'd put this number here and I would get 0.63174. If we add those two numbers together, I get 0.63214. So now I actually have a range of values that the sum of this series could add up to. And depending on the construction of the series, we don't know if that next term is a positive value or a negative value, and that's why you account for either case. And so we said, well, it's going to be somewhere in between there. And eventually, all the terms become 0. So that's why we only have to look at the next term, because we know they're steadily getting closer and closer and closer to 0. And if you look by term 7, look how many decimal places you have to go out to even get a number, right? So this thing is decreasing very rapidly, right? So I'm not going to ask you to do this on an exam or anything like that, but it is something you need to be aware of because, like I said, when we use series, especially anything involving computers and programming, remainders and things like that are very important, and there are ways to program these calculations into the system because these remainders are your errors. And if you're doing manufacturing and you're working with equipment that are building something and you need a margin of error like to be within 1%, there's a way that you can program to say, okay, I'm going to only deal with the first 6 terms because the remainder beyond that is only a 1% deviation from what I want. So there are ways you can use this stuff in other places. And then later when we get into Taylor series, you'll see that we use error terms and we realize, oh, well, we only need to look at the first 6 terms, 3 terms, and then we can dump the rest of the series because we're comfortable with the margin of error of a certain value, and it just allows you to reduce things from infinity down to a finite value that we can then work with. So this stuff is an important idea. All right. So the next thing we need to talk about when we talk about alternating series is absolute versus conditional convergence. So once again, remember, math nerds not really creative when they name things. So absolute convergence is going to involve taking the absolute value of something. That's a good way to do it. So absolute convergence. If the sum of the absolute value of all the n terms converges, then the original series converges. So why are we talking about that in this section? Well, there's no need to take the absolute value of a series if all the terms are already positive. But if the terms are alternating between positive and negative, what we're saying is, well, if we take the absolute value and make all the terms positive and we add them up, that's the maximum possible sum you could ever get out of the series. If that thing converges, well, then the alternating terms are going to have to converge because they're just going to add up to something less because you're going to give a little, take a little back, give a little, take a little back. So an alternating series will have a lower sum typically than the series if we remove the alternating terms. So everybody see that? So if you look at a really good way to look at that would be, right, we all know how to sum, right, 1 over 2 to the n. We know this sums to 2 when everything's positive. But if I alternate this series, right, this is 1 over 1 plus a half, which is 1 over 3 halves, which is 2/3. So the reason we get so much less of a sum is because we start with 1 and then we remove a half. And then we add in a third, and then we remove a fourth, right? So every time you add a little bit more to the pile, you then immediately take most of it back, or almost half of what you just added back. So very dramatically different sum. So that's why if we make all the terms positive and those converge, then we know by default the alternating series will have to converge as well, okay? So we call that absolute convergence, right? Because the absolute value converged, okay? So let's see why this is true. Right? So the a sub n terms, right, are all going to be 0. Are all going to be positive when we siphon off, oh God. I don't need this right now. Sorry guys, my cat might be. Sorry guys. Oh shit, my cat just got out. Okay. Never mind, we're all good. Our next door neighbor's cat looks almost exactly like my cat, and everyone who stays at my house freaks out and they think they've let him out, and then it's just, yeah, but she got him in. Okay. So the terms, right, are going to be positive, so that's where the greater than 0 comes in. But if we add, right, the absolute value, that makes everything positive here. So the result of this, right, will always be a sub n. So what we can say is this is less than or equal to 2 times this. So if you take the negative, if the term is negative, right, and you add it back to its absolute value, it's going to become positive, right? So if this were negative 1/2 plus positive 1/2, we would get 0. But if the term is positive 1/2 and you add it to positive 1/2, right, you would get 2 times positive 1/2. So that's what that inequality is saying. So then what we can say now is that if we sum this stuff right here, sorry, this is true for all n, this series converges by comparison okay? So we can use the comparison test and show that those two series, both converge. So furthermore, that should be one word, we can write the term a sub n, there's sort of an alternative way of seeing this. We can say that any term a sub n is equal to a sub n plus the absolute value, right, minus the absolute value. So this just seems like a really silly thing to write out, right? Why would you add something and then immediately take it away, right? Well, if I now sum both sides of this equation, what you get is the original series you were trying to prove absolute convergence on has to equal the sum of these terms minus the sum of these terms. And so we can say that the original series converges because earlier when we learned our property of series, we saw the sum or the difference of two convergent series also converges. So if you go back and look at those properties when we first started looking at summations, I said, well, let series A sum to A, let series B sum to B, and we said, well, if you add series A to series B, the answer was A plus B, right? And if we subtracted series B from series A, we saw that the answer came out to be A minus B. And that's what we're saying here. If we know these two things converge, then this thing has to converge, because if you add or subtract two convergent series from each other, you get a convergent series. And we actually did this on the quiz with the geometric series. That's why we're like, oh, this converges, we can split them up. So the other thing is you can't say, if a divergent series, right, sums to infinity, you can't say that infinity minus infinity is 0. You can't do that, because if you have two divergent series and you're trying to add or subtract them, well, what if one of them's growing faster than the other one? What if one of them's like 2n and your other series is n? Well, the 2n is growing to infinity at twice the rate as the other. So even though they both end up at infinity, one's getting there a lot faster. So we can't do this with divergent series. What we can say, however, is that if you have the sum of two things, right, and you split them apart, and you say, well, this is a geometric series, which I know converges, And this is in factorial, which I know diverges. If you add, because remember, all we're doing in a series is adding up terms. If you have a finite number, the convergent series, and you add it to an infinite sum, well, then it's going to add up to infinity. So you can say that the sum of a convergent and divergent series diverges, because the divergent series will blow up the sum of the whole thing, right? So we can say here, the sum of two convergent series also converges. And we can add a caveat just to know the sum of a convergent and divergent series diverges. Does that make sense? Right? You're just taking something and adding it to infinity, so you're going to get infinity out. And that's a good thing to know if you're trying to prove something converges. If you recognize, or diverges, if you recognize a convergent part, but you also know for a fact you have a divergent part, you can use this idea. All right. So, one last thing I want to mention. The theorem says, right, if you take all the positive terms, then the original term converges. However, the converse of the theorem is not true. And we know that already by looking at the harmonic series. So what we mean by the converse is you can't say because the alternating series converges that all the positive terms will converge, right? And the harmonic series, we already know 1 over n diverges. We've actually shown it diverges a couple of different ways. But the alternating harmonic series converges because we just did it when we showed that it converges using the alternating series test. So it was right there, right? That is the alternating harmonic series, and it passed the alternating series test. So just because an alternating series converges doesn't mean it's absolutely convergent. You have to actually do the absolute convergence test to see if it works. All right, so we have time for one last quick thing for the quiz. I want to define this so then when we come back Thursday, we can just do some examples and finish out this section. Right? So what do we mean by absolute versus conditional convergence? So absolute convergence, we already showed you take the absolute value. If it converges, everything converges. So we know that a series is absolutely convergent if its absolute value converges. Right? And the example we used, right, was -1 to the n over 2 to the n converges, right? The alternating series converged, and the series of positive terms converged. So there's an example of a series that is absolutely convergent. A series is conditionally,
I found something on the web about this conditionally. Check it out.
conditionally convergent if the original series converges, which in this case would be alternating, but the sum of the absolute terms diverges. So the condition on convergence that they're referring to in the name is the condition is that it had to alternate in order to get it to converge. So in our example here, would be -1 to the n over n converges, right? The alternating harmonic series converges, but the sum of the positive terms diverge. So there's an example of an absolutely convergent series and a conditionally convergent series. In fact, you'll see that P series, right, that diverge when P is, she's spelling diverge now. They diverge when you're between 0 and 1, but when you alternate them, they pass the alternating series test and converge. Because they're all positive when you remove the -1 away. The limit of all of those things go to 0, and the terms are in fact decreasing as you go to infinity. So those P series, okay, that were diverging are conditionally convergent if you alternate them. All right, so we'll stop there and then we'll do some more examples of how to test for absolute convergence on Thursday. So now we'll take our quiz. This happens every semester. Last semester too, every time I would say series, she would start just like, and it was P series, and I think she thought I was saying please Siri. Yep, there she goes again. So remember, this is on the comparison test. So you can do direct comparison or limit comparison. And a couple of them are tricky, so I'll be around if you need to ask me some questions.